Why do all planets revolve on the same plane? There are countless planetary systems in the cosmos like ours, with planets orbiting a host star. Our solar system is named after our sun, Sol, which is named from the Latin word for sun, solis, and anything related to the sun is called solar. Astronomers discovered that Mercury, Venus, Mars, and all of the planets in the solar system revolve in almost coplanar orbits as soon as they began to observe the night sky. How could that be? This required an explanation. As of today, we believe the reason is that the planets' orbits are coplanar because the planets originated during the formation of the solar system from a disk of dust that enveloped the sun. Because the disk of dust was a disk, everything developed in a plane, including the planets. But let's take a closer look at this. Hello and welcome to Z. Don't forget to subscribe and click the bell icon. According to the most recent research, all exoplanets are unique, and there are plenty of them out there. It rains diamonds on certain exoplanets. Some have an iron core, whereas others have an ice core. Exoplanets can rotate clockwise or anti-clockwise, quicker or slower, and they can be large or small in size. Some of them, with massive oceans on their surfaces, may be livable. Others, because they are so close to their host star, may be in a tidal destruction process that heats them up and causes severe volcanic activity. If there's one thing we've learned about planets, it's that they're all unique. But they all have one thing in common. All planets and exoplanets formed in an environment known as a circumstellar disk, which revolved around their host star. How is this even possible? Let us begin from the beginning. As an example, consider our solar system. A star is formed as a result of the dynamical collapse of a massive cloud of gas. Most likely, this massive cloud of gas was in a highly unstable equilibrium condition in which even minor perturbations in the gas might cause a gravitational collapse, causing the molecules to become denser and denser and the cloud to shrink as a whole. The incident that caused the cloud to collapse was most likely external to the cloud, which was otherwise in equilibrium between its sections. Scientists believe it was caused by the explosion of a nearby supernova, which is a massive star that reaches the end of its life and bursts, spewing its whole atmosphere into space. The quiet shock wave would then have provided the initial thrust to the cloud, demonstrating that the death of one star can result in the creation of another. The heat and energy from the collapse create pressure, which, when time passes and the cloud becomes dense enough, counteracts the influence of gravity, holding the system together. The star is essentially formed when a hydrostatic equilibrium is attained between these two forces, gravity and pressure. Stars are massive, hot gas balls formed by the collapse of massive clouds of initially cold gas. We believe that the vast majority of stars, including our sun, were born in this manner. What happens next is less definite, but we do know that there is a circumstellar disk surrounding the star at this point, and the material continues to fall around the star. We say around because free-falling matter does not descend in a straight path to the center, but instead rotates in progressively tighter spirals. The rotation of the sun and planets around their axes, as well as the revolution of planets and other things around the sun, are all remnants of this primordial vortex. The remaining material on the cloud's periphery, far from the star, continued to circle around the core. The material then settled into a thinner disk as a result of this spinning, which was simple yet amazing. This is a really basic physics notion that we are all familiar with. Take, for example, your washing machine. Fill it with dirty clothes, add the bleach, and click the start button. The laundry has started. You can now see the clothing whirling and orbiting around the center of the washing machine. The result of centrifugal force is that they are pushed towards the walls as they revolve. However, if you look closely, you will notice that they are not pushed in random directions. They are not randomly distributed, rather, they rotate in a disc-shaped zone. Essentially, your garments are orbiting in the same orbital plane as you. This is what happened to the materials surrounding the Sun billions of years ago. As a result of the conservation of angular momentum, the material thinned into a disk, and little things known as planetesimals began to form as a result of collisions. The planets as we know them were formed as a result of subsequent aggregations. Even today, the solar system's primary components orbit around our star on almost the same plane, known as the ecliptic. Excellent work! This is the most straightforward and elegant response to the basic question, why do planets in the solar system revolve in the same plane? However, our solar system is made up of more than only planets. With a telescope, you can easily see that our planetary system is populated by other smaller things. Asteroids, frozen bodies, and dust are examples. Scientists believe they are the oldest relics of the solar system's origin, the result of primordial aggregations that failed to grow into planets. Their orbits are more inclined than the ecliptic, indicating that these bodies were excluded from the primary formation mechanism along the spinning disk. The majority of this old space debris may be found in the main asteroid belt, which orbits the Sun between Mars and Jupiter. Asteroids range in size from Vesta, which has a diameter of around 329 miles, 530 kilometers, to things as small as 33 feet, 10 meters. The cumulative mass of all asteroids is less than that of Earth's moon. Some asteroids orbit Jupiter in front of and behind it. These are known as Trojan asteroids. Near-Earth objects, or NEOs for short, are asteroids that come close to Earth. NASA keeps a close eye on NEOs because they have the potential to be dangerous. In order to defend our world, space agencies are presently looking for techniques to deflect an asteroid's trajectory. Planetary defense is a complete field of astronomy and engineering. For example, the DART mission, launched in November 2021, will contact an asteroid on September 26, 2022, as an orbit demonstration of asteroid deflection. DART will basically impact the asteroid Didymos to change its speed and route. DART will be the first space mission in history to demonstrate asteroid deflection. We're excited to see whether it works. As a result, we realize that planets, on average, orbit in the same plane. But first, let's look closely at our solar system. Is it true that they all fly on the same plane? As Earthlings, we've made the plane in which the Earth revolves around the Sun our reference plane for the solar system. When perceived from the Earth's reference frame, the Sun seems to move around the Earth in a path that is slanted at 23.5 degrees with regard to the spin axis. The ecliptic is the name given to this journey. It indicates that the Earth's spin axis is 23.5 degrees tilted with regard to the plane of the Earth's solar orbit. If we place ourselves on the ecliptic, the Earth has an orbital inclination of 0 degrees, and the orbital inclinations of other solar system entities are measured relative to this. Mars, for example, has an orbital inclination of 1.8 and Mercury has a 7.0. Planets, as seen in this image, orbit the Sun in lovely circular orbits. Pluto's orbit, on the other hand, is considerably different. It's very elliptical, circling the Sun in a squashed circle. Pluto's orbit is also strongly inclined, with an angle of 17 degrees. Pluto has various peculiar properties as a result of its odd orbit. It orbits so widely, for example, that it can swap places with Neptune, orbiting closer to the Sun. This happened the last time on February 7, 1979. Until February 11, 1999, Pluto was closer to the Sun than Neptune. and the last time this happened was in the 1700s. Pluto's orbit is very turbulent due to its low mass and interactions with Neptune. This means that predicting where Pluto will be in the following millions of years is difficult for astronomers since uncertainties accumulate, and it's hard to tell where it'll be in the remote future. To summarize, we may say that what we see in the cosmos now is the consequence of physical processes that occurred over billions of years. On the one hand, basic physical reasons can be provided to explain why both planetary systems and other objects, such as spiral galaxies, have the shape of a disk. On the other hand, scientists recognize that we live in a non-deterministic cosmos that is highly chaotic. This means that even the smallest perturbation in a system might produce unexpected outcomes. As a result, we can have planets with highly inclined orbits, like as Pluto, or unusual structures in the fabric of a galaxy, such as a moon-planet system. For instance, did you realize that the moon is gradually migrating away from Earth? The impacts of chaos, on the other hand, can only be seen over very long durations. I mean, chaotic occurrences occur all the time, but their impacts are essentially insignificant across human lifetime frames. This is good for us humans because, given our brief lifespan in comparison to the age of the universe, we can treat the phenomena as quasi-static and imagine, if only for a second, that we can forecast the behavior of the universe. This is all for now. Thank you for being with us.